Good morning, everyone. Welcome to Chemistry with Professor John. All right. Today we'll finish up the alcohol and phenols chapters. In the last video, we got it to about right here, which is turning alcohol into alkoxide. So there's a few different ways you can do that. Either using alkaline metals like potassium or sodium for the alcohol that have a regular pKa of about around 16. But when you get to phenol with a pKa about 10, that's a lot stronger. That's 10 to the 6 times stronger. That's 1,000,000 times stronger. You don't need sodium or potassium or sodium hydride. You need just sodium hydroxide. It's good enough to pull that hydrogen off. So to make alkoxide. And remember, alkoxides are really good nucleophile, as long as they're not bulky like this one is. This one is bulky, so this is not a good nucleophile. This is bulky, not good nucleophile. Okay, except that one, but other than that, we have all these guys are good nucleophile. Okay, so we're going to be using them to synthesize alcohol. All right. Now this is the Grignard reagents. When you take a CH3I or any R, X, and X is iodide or Br. Those are the most popular one. I'm sure you can work with Cl chloro as well. And you can see right here the reactivity trend. Now, if you take a alkyl halide and you put in magnesium neutral, that's what that 0 means, and ether as a solvent, and you turn that into a Grignard reagent, and they are extremely good. Okay, so you got the carbon right here. You got the carbon right there. Okay, that's negative because magnesium is, just think about magnesium is positive. Okay, so that will be a good one. You can also use lithium. Lithium is positive 1, so the carbon there is, you can think about that as negative 1. Now, if we take that R, okay, whether it's methyl, methyl, ethyl, benzene, or whatever you want, or even a cycloalkane. So we take that, okay, that's going to be carbanion, do a nucleophilic addition to a carbonyl carbon, that's positive carbon, that oxygen turn into an O minus, and then pronate it to become an alcohol. Now, we can control the carbonyl compound. If you got 2 hydrogens, that's formaldehyde, that's the simplest aldehyde, you get yourself a primary alcohol. 2-step, remember 2-step, okay? If you go with 1 branch, then you get secondary. You go with 2 branches, it doesn't have to be methyl, it's just something with carbon, you get tertiary alcohol. Okay, so how would, I write that on the test, right? So on the test, I would do something like Br, and then I will go step 1, Mg ether, and then step 2, I'm going to put in for example, a ketone, and then step 3, I'm going to do H3O+. You guys see it? Now with that, your product will be the ketone now become OH, and your ethyl will be added to the ketone, right? Okay, so that's how we do it. All right, so that's what you see, and our job is to be able to predict the products, the final products. Mechanism pretty straightforward. Okay, as you can see right here, this is the mechanism. It shows us how it happens. Okay, now we can also add to stronger receiver, the carbonyl compound receiver, like acid chloride, okay, or ester. Okay, acid chloride is very popular. Okay, so when you do acid chloride, it's gonna happen twice. Okay, the first one, O minus, instead of getting protonated, it can go back and reform the double bond, and chloride take off, and then we got a ketone. Okay, and then pretty much now repeating. We do the second time, just like previous reactions. We add it to the ketone, so we would need 2 excess Grignard reagents. So we end up with 2, okay? And then protonated, get the tertiary alcohol. So this is a good way to make tertiary alcohol, okay? The alcohol, the carbon is bonded to 3 other carbons. Okay, so that's Grignard reagents. Now we can also add it to same Grignard reagent to epoxide. And remember, to make epoxide, all you need is a double bond and per acid. That's MCPBA. Go back to alkene chapters, and you should be able to see it. CH2CO2 as a solvent, and you got epoxide. And this is the simplest epoxide. It doesn't have to be that one. Any cyclopropane ring with a oxygens. Okay, so that will open up, and now, that's right. That's a bond. And then so that's O minus. Pick up the hydrogen, become OH. So with the simplest epoxide, we get primary alcohol. Okay, now these are not something to worry about. It is something that we want to avoid using this compound because of the OH. So the carbon will go after the hydrogens, okay, and instead of going after the one that we want, the carbonyl carbon. Okay. Now there's other way. We don't have to use Grignard reagents. It's just a good reaction to make an alcohol with more carbon, increase the carbon chains. Okay, so we can use reduction reactions, like we have sodium borohydride, and ethanol is the solvent. So with sodium borohydride, give us a lot of hydride, H minus, added to the carbon of the double bond, and then oxygen pick up the hydrogen from water or alcohol to become an alcohol. And we can control what we want. If you use aldehyde, you get primary. You use ketone, you get secondary. Okay. So aldehyde give you primary, ketone give you secondary alcohol. And notice that the ester stay the same. So this one right here, only that. Okay. Do you notice that double bond right here? stay the same. That's ester. Four. Same for carboxylic acid. Okay. Now, if you want to reduce those, we have to use something stronger. That's lithium aluminum hydride. Can reduce both carboxylic acid and ester. Everything. Acid chloride as well. Okay, into primary alcohol. All right. Now, and of course that's gone. Okay, as if you care for it. Okay, but that's not the main compound. Now, with Ranny nickel is actually a mixture of, it's an alloy of nickel and aluminum, and it's really cool. They can reduce double bond, triple bond, aldehyde ketone. Okay, all together. But still, not carboxylic acid or ester or acid chloride or amide. That's only lithium aluminum hydride. Okay, and notice that sodium boron hydride can only reduce the alcohol. I mean the C double bond O of the ketone or aldehyde. Okay, how about reactions? There's quite some reactions. The first one is oxidations, and we got two different kinds of alcohol, primary and secondary. Now, primary, there is a difference. If we use a mild reducing agents, which is PCC, there's two mild reducing agents. Okay, PCC is one, and the other one is SWON. Okay, now if you use PCC, that's mild. We got an aldehyde. If we use strong reducing agent, we got carboxylic acid. That's sodium dichromate in sulfuric acid. Now in the solution, sodium dichromate react and form chromic acid first, and chromic acid is actually the oxidizer, the active oxidizer that oxidize primary alcohol to carboxylic acid. Okay, so remember that. PCC versus sodium dichromate in sulfuric acid. Now, if you have a secondary, it doesn't matter what you use. You use PCC or you use PCC or sodium dichromate, you always end up with a ketone because there's no more room to add the OH. Okay, that's already carbon, already has 4 bonds. All right. And then you got the byproducts. Now, tertiary alcohol, no reactions for tertiary alcohol. There's no space for it. Okay, we also have other oxidizer or oxidizing agents. These two are strong. Okay, strong oxidizer. So you notice this, you form carboxylic acid. For secondary alcohol, it doesn't matter. We always get a ketone, strong or mild. SWON is also a mild oxidizer. So for secondary, we get a ketone, but for primary, we got aldehyde. So we do have a lot of options there, okay? Either SWON or PCC, remember, okay? PCC or SWON, primary to aldehyde, okay? Only. All right. Now, okay, so that's oxidations, reactions. Now, OH is really cool. Um, okay, it's really actually hard to get rid of the OH. I mean, we can get rid of the OH by putting in acid and then heat it up, and it's dehydration to make an alkene. If you've probably seen that in alkene reactions, right? Alkene synthesis. Now, another way to get rid of the OH is to tosylate it, meaning react with tosyl chloride to turn that into a tosylate. That's called, this is known as the tosylate. That's the tosylate right there, okay? And it turns out tosylate can take off by itself, just like good Leeuwenhoek. Like Cl or Br, iodide or Br. Okay, so good Leeuwenhoek, so to take off, you can replace it. So if you put in a nucleophile, you can kick out the OTS, just like that. Okay, so you got so many options. Okay, especially the last one is really cool. Replace OTS by hydrogens. So in the end, we just want to get rid of the OH. Okay, so basically, if you and here's more replacements, and just like typical SN2, you start out with S, you get the R. You start out with R, you get the S. Now here's the really cool stuff. Okay, OTS become OH become OTS, and that's it. Sodium boron hydride, lithium aluminum hydride give us 4 hydride minus, and hydride minus come in, kick out the OTS, so we got just cyclohexane. Or we can also replace it with replace the OTS with halogens like bromine. A couple of examples for you to see. You can convert alcohol into alkyl halide, which either OTS or just acid, HBr, and mechanisms, very simple mechanisms, substitutions. For tertiary alcohol, obviously tertiary is SN1, and this is a good reaction to identify secondary alcohol. Is the fastest one compared to primary alcohol. What happened with Lucas for the tertiary? I wonder. Okay, that's what we got to find out. But look like here it show Lucas compare fast reaction for secondary versus low reaction for the primary. So that's a good difference for us to identify. Okay. Identify the what type of alcohol. We can also do iodinations, or that would be replacing the OH with the iodide. Now HI doesn't react, but we can also use PI3. Like in this case right here, if you want to make replace the alcohol with the iodide, and iodide is an excellent Leeuwenhoek, of course. Here's a couple of examples. We want to replace with iodide. It looks like here we have a primary. Now mechanisms should be very straightforward. Okay, SOCl2 is a good one. Alternative for alcohol, like primary or secondary alcohol. We want to replace the OH with the chloride. And notice that the reaction happened just a simple replacement, and it's just a simple transferring. So it does not. It's not like an SN2, so it doesn't affect the stereochemistry. So that's 100%, in theory, the retention of stereochemistry. Here are some of the summary of substitutions, and for different type of alcohol, primary, secondary, or tertiary, and what's best to use. Notice it's tertiary. We use because it's simple, SN1 replacement. So we use acid, HCl, HBr, or iodide. Okay, there's a couple additional problem for us to practice, and then let me know if you guys have any questions. All right, thank you all.